Welcome to The Explainer. Today, we're going to pull back the curtain on the incredible manufacturing journey of one of the most essential yet totally invisible components in all of modern electronics, the quartz crystal.
So how does it work? How does your phone keep such perfect time? Well, the secret lies inside a tiny, precisely engineered component. Today, we're following its unbelievable journey from a simple raw material to a finished product. It's a story of some seriously extreme engineering that turns basic silica into the stable, reliable heart of our entire digital world.
Okay, here's the game plan. Our journey has 6 main stages. We'll start with creating the perfect crystal, then the art of the cut, some microscopic sculpting, getting the electrodes on, sealing it all up for stability, and finally, inspecting it for absolute perfection.
All right, let's kick things off. It all starts not by mining something out of the ground, but by growing a quartz crystal that is way, way purer than anything you'd ever find in nature. The whole point is to create a perfect atomic lattice, totally free from the defects and impurities that would throw off its timing.
So how do they do it? Well, engineers basically copy what the Earth does over millions of years, but they do it in a lab using a process called hydrothermal synthesis. They take raw silica, dissolve it in a super hot, high-pressure chamber, and then let that solution rise to a cooler spot, where it ever so carefully deposits, molecule by molecule, onto a tiny, ultra-pure seed crystal, making it grow over time.
And the environment for this whole process is just extreme. We're talking about temperatures hotter than a pizza oven and pressures that are greater than what you'd find at the bottom of the Mariana Trench. It's wild. But you need those conditions to dissolve the silica and grow these perfect crystal boules. And the whole thing can take up to 2 months.
Okay, so once we have a perfect crystal, it has to be sliced into these paper-thin wafers. And this is what we call the art of the cut, because the angle is absolutely everything. This is where the crystal really gets its personality and its performance is defined.
Now, slicing these incredibly hard crystals is a serious challenge. The old methods, using these inner diameter saws, were super wasteful, and they actually damaged the crystal structure. But today, modern wire saws use a super thin wire with a gritty slurry to slice wafers with just incredible precision. It minimizes waste and creates a nearly perfect flat surface that barely needs any polishing.
And that angle of the cut we mentioned, it is so critical. The common AT cut, for instance, gives you great stability for general purpose stuff, like in a TCXO. But for something that needs to be ridiculously precise, like in an oven-controlled crystal oscillator for a cell tower, you need an SC cut. That stands for stress compensated. And that classic 32.768 kilohertz frequency in your watch, that comes from a tiny little tuning fork-shaped XY cut.
Now we zoom way in, to the microscopic level. The wafer has the right angle, but now it needs to be sculpted into its final shape, with the kind of precision that's almost hard to wrap your head around.
This is all done using photolithography, which is the exact same process they use to make computer chips. First, they coat the wafer with this light-sensitive film. Then a pattern is zapped onto it with UV light. A developer then washes parts of that film away, and what you're left with is a perfect microscopic stencil to guide the next step.
That stencil, or mask, protects the crystal during etching. That's where material is chemically eaten away to get the exact thickness for the target frequency. Now, wet etching is fast and cheap, but it kind of etches in all directions. For creating super fine, perfectly vertical walls with the ultimate precision, engineers use dry plasma etching, which uses a reactive gas to basically bombard the surface.
So the crystal now has the perfect shape, but right now it's just a passive piece of quartz. To make it vibrate, to actually bring it to life, it needs metal electrodes to apply an electric field.
And the choice of metal is critical. It's not random at all. Each one offers a different trade-off. Gold is what you pick for its chemical resistance, for harsh environments. Aluminum offers great stability at high temperatures. And if you need the absolute maximum energy efficiency, what engineers call a high Q factor, then silver is your best bet. And this metal gets deposited in a high vacuum to make sure the bond is totally pure and perfect.
And here's the really clever part. Adding these electrodes also does something else. It tunes the frequency. That first layer of metal actually adds mass, so it lowers the crystal's frequency a little bit. Then, the engineers go back and deposit a tiny, precisely controlled amount of more metal, usually gold, to nudge the frequency right back up to the exact target. It's just a process of mind-bogglingly small adjustments.
A finished crystal is so sensitive to its environment. I mean, even a single speck of dust or a tiny change in air pressure can throw off its frequency. So, protecting it is the next absolutely critical step.
And this quote from our source material just drives the point home perfectly. For those super high-performance crystals, like the SC cut, they are so sensitive that they must be sealed in a vacuum to work right. Any little leak would just completely ruin their performance.
You know, long-term stability, or what's known as aging, is this constant battle. The frequency can drift over years because of contaminants, or stress from the mounting, or even how much power you use to drive it. To fight this, manufacturers use hermetic welding, special stress-compensating designs, and they filled a package with an inert gas, all to make sure your devices stay accurate for years and years to come.
Finally, before a crystal can become the heartbeat of your device, it has to survive a battery of brutal tests to make sure it is truly perfect. And adherence to strict industry standards here is completely non-negotiable. This means passing military-grade specs for tough environments, undergoing fine leak tests with helium to check the seal, and a burn-in process where the crystal is basically pre-aged at high temperatures. This forces the biggest frequency drift to happen at the factory, not in your device.
So, from a high-pressure autoclave all the way to a microscopically sculpted and perfectly sealed component, the journey of a quartz crystal is an incredible testament to precision engineering. It's a reminder of all the complex, invisible technology that powers our world, hiding right under our fingertips. Makes you wonder, what other invisible marvels are hiding in plain sight?